Hello again. Thanks for joining us. This is Space Nuts Q&A edition. My name is Andrew Dunkley. This will be our last official show for 2025. We'll go into a short recess and be back with you early in the new year. But we've got some questions to nail down before any of that happens, and we've got a whole bunch of topics that seem to have stirred the imaginations of our audience. Andrew wants to know about time dilation of stars. Adriano is talking black holes becoming stars. Ishtok is wanting to ask about free space. I always thought it was expensive, especially all the space around where we live. Yow. And Gergo, redshift and gravastars. We will tackle all of that in this edition of Space Nuts.
15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2. 1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
And here he is again. It's Professor Fred Watson, astronomer at large. Hello, Fred.
Hello, Andrew.
Good to see you again.
Fancy seeing you.
Yeah, how odd. How strange.
How strange.
Getting ready for your Christmas break. I mean, you've just come back from a break, so you'd be, probably feeling rather relaxed.
Well, no, because only the last 6 days won't work. Yeah. So, no, it's not quite true because we did have some time off with my family in Scotland. But we did have a proper holiday at the end of our trip. But yes, we did 2 months of pretty hard work, actually. We had a tour in Japan and then a conference in Ireland and a few other things like that kept us busy. So
if you want to call international travel a job, that's fine. I want to call it work.
But when you've got a tour group, when you've got 20 people who you've
that's how it works.
Entertained for a month, it's actually 3.5 weeks. It is work.
Yeah. Well, we've got a similar problem in the coming week or two with 4 grandchildren that we're taking to the coast. Yeah.
To be honest, I'd rather have 20 tourists than 4 grandchildren. Although my grandchildren are now totally self-propelled. Apart from the youngest one, Aggie, she's 9 months. Yesterday, actually. Anyway, yes. It's a matter of, So when the bottom line is, we will have a relaxing end of year break. I hope.
Very good. You mentioned Edinburgh. Well, our first question comes from Andrew in Edinburgh. He says, I have a 2-part question about the gravity and subsequent time dilation that occurs in and around supergiant stars. If the supergiants can collapse into black holes, then they must have as much or even more mass than the resulting black hole, just spread over a much larger area. I guess my question is there significant time dilation near these stars, or are they simply not dense enough to have meaningful amounts of time dilation? If they do, it's weird that it never comes up. And a slight follow-up would be, what about time dilation within the star itself? Presumably near the core of these stars, the density ramps right up. Does a large difference in time dilation within a star have any impact on how it behaves? Hope that all makes sense. Thanks. Love the show. That's Andrew in Edinburgh.
They're great questions. I'm just not sure about the first sentence. If the supergiants can collapse into black holes, then they must have as much or even more mass than the resulting black hole. Yeah, okay, I've read that properly now. Just spread over.
Maybe I didn't read it properly.
No, it's all right. No, it's fine. So Andrew's first question, is there significant time dilation near these stars? And the answer is yes. There would be. The time dilation in a black hole is so great that to an outside observer, time stops on the event horizon. For a star, because it's spread over a larger volume of space, the time dilation is nowhere near as great. But time dilation would be something that you would have to take into account if you had a spacecraft orbiting near a giant star. The bottom line is, with time dilation, it's a little bit spooky in the sense that to the star itself and to something, say you've got something in orbit around this star, their time's ticking away at the normal rate. The time dilation is only what you see from the outside.
So this is basically the same as we were talking about in the last episode regarding Mars. Same problem.
Yes, that's right. It is the same thing. Yeah. So time ticks away normally for the star, but to watch it from the outside, you basically see time ticking away a little bit more slowly. So they would have time dilation. And Andrew's asking whether they're not simply not dense enough to have a meaningful amount of time dilation. And I don't think that's true. I think that this time dilation is significant, especially if you're looking at microseconds, as we were in the last episode. So they do. And look, you're not talking about time dilation of the kind that was depicted in Interstellar, where time kind of grinds to a halt almost. It's a more modest amount of time dilation, but it would actually happen. And Andrew's follow-up question: what about time dilation within the star itself? Presumably near the core of these stars, the density ramps right up. There's a large difference in time dilation. I'm not
going in there to find out.
Does a large difference in time dilation within a star have any impact on how it behaves? And there's a curious thing there, because as you get nearer the core of an object with spherical symmetry, your gravitational field gets less and less. And in fact, at the center, you wouldn't feel any gravity. And that's because everything's pulling you in the same direction all around. And I believe that time dilation will probably stop in the middle of a star. That might be right. So it's something I've never thought about before. Maybe that's not true, because you're still in a gravitational field. The fact that it cancels out everywhere. I'll check that one out, actually, and try and remember for our first show next year, because that's a really interesting question. Time dilation in the center of a star. How does it behave?
Yeah, very interesting.
But there wouldn't be I think the bottom line is there wouldn't be a big difference in time dilation from one part of a star to another. That's what I'm trying to say.
But he brings up another interesting point. You've got time dilation around a massive star.
Yep.
Then it goes, whatever, black hole. The time dilation changes?
Yes, it does, because as it collapses, the gravitational field increases. It increases in sort of angle, in the sense that it's a steeper gravitational field as the black hole collapses. And by that, I'm thinking of the gravitational well. This dip in the trampoline sheet, that's the gravitational well of an object, which turns into something like a plug hole with water going around it as a vortex for a black hole. So that's what I mean by the steepness of the gravitational field. And yes, it is so steep that the event horizon delineates where the time dilation becomes such that time appears to stop on the surface of the event horizon.
Yeah, I've seen that demonstration done with like a big rubber sheet, and they say that's the space-time continuum. Then they put a bowling ball in it, and they say, and that's gravity.
Yeah, that's right. Yep, I know.
Yeah. It's a simple way of explaining it, but that's what it is, I suppose. Great questions, Andrew, and I hope all is well in Edinburgh, Fred's home stomping ground.
Yep.
Yeah, I'll give you his address and you can go and rock his roof. This is Space Nuts with Andrew Dunkley and Professor Fred Watson. We have got an audio question. Fred, this is from Adriano.
Hi guys, Adriano from Florence in Italy. I have my first question about black holes. So if I understood correctly, a star continues to burn his fuel like hydrogen and helium, and there are nuclear fusions, and there is enough energy for the star to fight against its own gravitational pull. But at some point, there is not enough fuel, and the star collapses into a black hole. After this, the black hole will start to absorb material like hydrogen, and then it should have enough energy, enough fuel to have nuclear fusions and to fight against the gravitational pull. But so why a black hole cannot turn back into a star? I'm sure this is not possible, but I cannot understand why. And also, guys, we had a lot of beautiful updates from the princess. Can we also have some updates from Fred? Thank you, guys. Bye-bye.
Adriano, thank you very much. Fred gave us his update when he got back. But yeah, your point is well made. Florence, what a beautiful, beautiful city.
Yeah, isn't it just?
We visited Florence a few years ago, and it was amazing, but it was also terrible timing because it was All Saints weekend, which is a 4-day long weekend, and there were like tens of thousands of people there. You couldn't move. You absolutely couldn't move. So we went to, what was it called, the Ponte Vecchia, and we couldn't get near it. You just couldn't. It was insane. Yeah, we didn't know until we got there that's what was happening. But yeah, we still got to see it. It was a beautiful place, and all those amazing statues. And Galileo got up close with Galileo.
Very good, yeah.
Yeah.
Did you see his? I think it's one of his fingers or his thumb. I can't remember, which is on display in the Science Museum there.
Oh no, couldn't get near that.
Yeah,
honestly, it was just mayhem. But yeah, understandable though. All right. So the bottom line with Adriano's question is, why can't a black hole turn back into a star?
Yeah,
I would think there'd be all sorts of reasons why not.
Well, that's right. I think once you've turned into a singularity, as the
you can't double down. Boom, boom. Sorry.
You took the words out of my mouth. No, you didn't. I mean, all bets are off basically once you've gone into a singularity, and so I think it's a great thought that Adriano's had. It's never occurred to me before, but you're talking about hydrogen, which certainly would get sucked into a black hole because a lot of the gas clouds that a black hole accretion disk would draw in and suck into the center. That's hydrogen, and hydrogen's the raw material of stars. Why can't nuclear fusion kick in again and drive the star back into being a star rather than a black hole? And I think the answer is in structure. So stars have quite a complex structure to make them work, with the core, with all the nuclear burning taking place. Then there's a convection zone, and then there's a sort of outer layer before you get to the photosphere, the layer that you can see. When you've put something into a singularity, all structure disappears, and it almost relates to an issue that occupied the mind of Stephen Hawking for a while, which is that does information get lost when it goes into a black hole? And I think there was some argument with another well-known physicist. In fact, I think they had a bet, which Hawking lost, because I think the bottom line was Hawking bet that information couldn't come out of a black hole, but somebody proved a theory that information could come out of a black hole. I think I've got the right way around.
Okay.
But basically, it's all completely mangled in terms of, we don't understand the physics of what would happen inside a singularity. We just have no idea what the physical processes would be. And they almost certainly would rule out hydrogen atoms getting together and with enough temperature to produce the nuclear fusion that we see in a normal star. A black hole is a very abnormal object. Nothing relates to normal in a black hole, and so I think that is the answer to Adriano's question. Physics doesn't work the way it works on the outside of a black hole, and I think that's why we don't see black holes turning into stars.
Yeah. Well, there's also the fuel issue. Like, the star has collapsed because of fuel depletion, has it not?
Yes, that's right. But what we're saying, and what Adriano's saying, is that among the stuff that is accreted by the black hole when it's sitting there gobbling stuff up, a lot of that is hydrogen, which is the fuel. So they're getting more fuel, but they don't any longer have the process to make it turn into something that will deliver energy. Indeed. I think that's the bottom line.
I get it. Okay. Great question, though, because we've been talking black holes for I don't know how long, probably since the very beginning of the time that this podcast began. And I don't think we've ever been asked that question before.
No, I think that's right.
Yeah.
Says a lot for our listeners, doesn't it? That they can produce questions that we've never had before after however many episodes is it? It's getting on for 500 now, isn't it?
This is 582.
Oh, 582. Okay.
582. Yeah.
Right, there you go, getting on for 600.
I don't know. It's nuts. I mean, it's happening faster because of time dilation and the fact that we decided to do 2 episodes a week instead of 1. But
but I think it's nuts by definition, isn't it? I've got a feeling.
probably.
Yeah.
Anyway, thank you, Adriano, and hope all is well in the beautiful Florence. This is Space Nuts with Andrew Dunkley and Professor Fred Watson. Let's take a break from the show to tell you about our sponsor, Anti-Gravity A1. Have you ever wished you could actually feel what it's like to fly? Not just control a drone from the ground, but truly experience the air around you. Well, that future has just arrived. Introducing the Anti-Gravity A1, the world's first all-in-one 8K 360 drone. And it's officially available now. This isn't just another drone. It's an entirely new category. With Anti-Gravity A1, you don't fly by fiddling with sticks. You fly with your hands and your head. The vision goggles use ultra-sharp dual micro OLED displays, and the grip controller's free motion lets you literally point where you want to go. Look left, the drone looks left. Tilt your hand, it responds instantly. It's the most intuitive flight system ever created, easy for beginners, but still offering full FPV controls for seasoned pilots. The Anti-Gravity A1 is now available in 3 bundles at the Anti-Gravity store, Best Buy and authorised retailers worldwide. So if you ever wanted to rethink what a drone can be or what flight can feel like, check out the Anti-Gravity A1. Just visit antigravity.tech. That's antigravity.tech for the Anti-Gravity A1. This is a new revolution in drone and drone photography. That's antigravity.tech, or you can tap on the link in the show notes.
3, 2, 1.
Space Nuts.
Our next question doesn't come from Italy. It comes from Slovenia.
Right next door.
Yeah. I am listening to your podcast while driving to and from work. Great show. I hope you manage to keep control because, this gets a bit crazy sometimes. I'm curious about, wait for it, Fred, black holes. We know that an atom is actually a lot of free space where electrons fly around. Eliminating that, we probably get a neutron star with high density. But what about a black hole? How does this work? Where is the free space that can be squeezed even further to get a black hole, get black hole material and density? And to calculate the density of the black hole, would it be a correct assumption to take the event horizon as the boundary and based on that, calculate the volume? Or is it something else? Thank you. Best regards, Ishtok. Another black hole question. Not surprising. We get a lot of them.
We do, yeah. So it's a great question, and that's absolutely right. An atom is a lot of free space, empty space, with a cloud of electrons doing their quantum thing. If you collapse the space down so that only the electrons are pushing the atoms apart, you've got a white dwarf star, which is called electron degenerate. And if you get rid of the electrons, then you get a neutron star, exactly as Ishtok says, with very high density, where only the neutrons keep the thing from collapsing into a black hole. But with a black hole, the free space is basically disappeared down the black hole. In terms of its density, you have a definition of a black hole. One of the definitions is a point in space with infinite density. So the volume is zero. See, Geordie thinks that as well.
He does.
Gosh, I don't know what's happening out there, but yeah.
I love it. Oh, we had to hear him from for the last show of the year, didn't we?
Last show of the year, that's right. In full flight. So it's a point of infinite density. So Ishtok's comment about calculating the density of the black hole, would it be a correct assumption to take the event horizon as the boundary? No, it wouldn't. The event horizon's just that imaginary point of no return, and the volume is zero. the volume of the black hole is zero, which is how the density gets infinite, because mass over volume is density. The mass is a parameter, but the volume is zero. I've no idea what's happening out there, Andrew, with Geordie, but he obviously likes this conversation.
Yes, he does. He wants in.
Yeah.
Oh, dear. Look, I still don't get black holes.
It's receding into the distance.
It is.
Very close.
Yeah, probably chasing a snake. Yeah.
Go ahead, Andrew.
No, it's hard to get your head around something like a black hole having no density.
No volume.
No volume.
So it's got no size. It's got zero dimensions.
I mean, we give them names based on size, and yet it has no size.
Supermassive. Yeah, well, but it's the mass. That's the thing. So the mass is defined for a black hole. It's one of the properties that they have. There's this thing called the no-hair theorem, which I like very much.
Yeah.
And it's about,
Would they?
Yeah, that's right. Which is, it's about the very few parameters that you can get from a black hole. I think it's mass, charge, and spin. I think that's all you know about a black hole. Because the volume's zero, and that's why the density is zero. Density is mass over volume, volume zero, so the density goes to infinity. But you can vary the mass, and that's why we talk about supermassive black holes and intermediate mass black holes and things of that sort.
Okay. So what was the answer to the question?
No.
Righto.
What was the question again? Hang on. Would it be correct assumption to take the event horizon as a boundary and use that to calculate the volume? No. The event horizon is an imaginary sphere that is where the thing turns black, basically, because no light can escape.
Precisely. Hope that helped, Ishak.
It's a great question.
It is. Terrific question. Just a very difficult subject, because we just don't know a hell of a lot about black holes. They're just such a mysterious and weird object, and we're still trying to gather information about them, and they just keep throwing up these curveballs at us and not letting us in. Not that you want to go in, but you know what I mean.
Yes, that's right.
Yeah.
Quite so.
All right. Thanks, Ishtok. Time to take a break from the show to tell you about our sponsor, NordVPN. If you're online, your data is always at risk unless you take some sort of action to secure your exposure. And a virtual private network is the way to go. There are lots of hackers and trackers and unsecured networks out there that just make you an easy target. And it happens without your knowledge. It always happens very quietly and in the background. And that's what makes it so nasty. And that is also why using a trusted VPN like NordVPN is a pretty smart move. NordVPN keeps your internet connection secure and private by encrypting your data and hiding your IP address. And that means you can browse, you can stream, you can shop, you can work online without worrying about who might be watching. And right now, as a Space Nuts listener, you can get an exclusive offer, big savings on NordVPN plans, get an extra 4 months for free. That's 28 months. And all you have to do is sign up. Don't forget, they've got a 30-day money-back guarantee, so you can test this out for yourself before you fully commit. But I've been using it for years now, and I've got no complaints. So go to nordvpn.com/spacenuts, nordvpn.com/spacenuts. And don't forget the code word Space Nuts at the checkout.
Space Nuts.
We have one more question to finish things off for 2025, and it's a real European flavour for this episode. This is Gergo.
Greetings, gentlemen. Gergo from Slovakia here. I have a question about redshifting. Does it have a limit? Is there a point beyond which light cannot be stretched any further? If so, what happens if the light continues to travel through expanding space? And the second question, could you talk a bit about Gravastars? Do you think they might be real? Thank you for your time and for the great show. Bye.
Thanks, Gergo. It's an eclectic mix of nationalities. This
Fabulous.
it's terrific.
Yes, great.
So 2 questions he's thrown into the mix. Is there a limit on redshift? Good one.
So, it is a good question. I mean, so redshift as a term we define as being due to the expansion of the universe, and it's slightly different from the Doppler shift. Doppler shift is something we understand well. It's the way the light changes wavelength from a moving object. But with redshift, we're talking about space itself rather than objects moving through space. We're talking about the way space behaves. And so it's a much more fundamental thing than the Doppler shift. So in a sense, there's already a limit to redshift, but it's one that is exactly related to the age of the universe. So what I'm thinking of here is the cosmic microwave background radiation. That's the wall of radiation which corresponds to the brightness of the Big Bang fireball, which we're still seeing because as we look further into space, we look back in time. So everywhere in space, we see this wall of radiation, which is now in the microwave region of the spectrum, which is why we call it the cosmic microwave background radiation.
Yeah.
And so it's, if I remember rightly, that is basically the visible flash of the Big Bang, because it was basically a visible light flash. It's the visible flash redshifted by, I think, about 1,300 times. So everything in the universe that we can observe must have a redshift less than that. I think 1,300 is the number that comes into my mind. I've looked at this for a long time. But it's visible light whose waves have been stretched by that amount to give us microwaves. So it's stretched about 1,300 times, thereabouts. Now, as the universe expands and time goes on, that number will increase. Not by much, might become 1,301 or 1,305, but as time goes on, that number's increasing. So in a sense, that's a limit to redshift. Physically, though, I don't think there is a limit. You could, if you expand the universe, if you're talking about 40 billion years into the future and the universe is expanding more, yes, the cosmic microwave background is going to be the cosmic long wavelength radio background. And so the wavelength will have stretched more. So there isn't a physical limit, but there is a limit in the real universe, simply because of the age of the universe. The universe hasn't expanded for long enough for the redshift to be more than about 1,300.
Right. Okay. Yeah, got it.
Good. What was the other thing? Gravastars.
Oh, Gravastars. Yeah, we've had questions about Gravastars before, more than once. It seems to be something that sort of captured the imagination of people that are so interested in astronomy and space science. So I suppose we should start by reminding people what a Gravistar is supposed to be, because I don't think we've ever found one.
No, that's correct. I'm going to read from that font of all knowledge, Wikipedia, who I do subscribe to, despite the fact that they keep asking me for another subscription. Anyway, that's probably because I've got more than one username. Never mind. Let me read from Wikipedia. In astrophysics, a gravistar, which is a blend word of gravitational vacuum star, is an object hypothesized in a 2001 paper by Pavel O. Mazur and Emil Motola as an alternative to the black hole theory. Oh. It has the usual black hole metric outside of the horizon, and a metric is just a way of describing space, but de Sitter metric inside, and that's a different one. Don't worry about that. A typical gravistar is as big as London, but weighs 10 solar masses.
Why?
Yeah, so a neutron star would be about the size of London, but weigh one solar mass, basically.
Didn't they find one in a sewer? They called it a fatberg or something.
Fatberg, that's right, yeah. Which was just about to turn into a Gravastar.
Yes.
On the horizon, there is an ultra-thin, incredibly tight shell of entirely new, unique, exotic matter named galactic flubber.
I was close.
You weren't far off, that's right, which is the next thing to a fatberg, yeah. Anyway, continuing to read. This solution to the Einstein equations is stable and has no singularities, which we've just been talking about, singularities, points of zero volume. Instead, a Gravastar is filled with either dark energy or with vacuum energy, but also vacuum. Only the inside one 10 to the 44 times denser than the outside. I'm not sure how you can have a vacuum that's 10 to the 44 times denser than another one, but I'll just let that pass.
Yes.
As a bonus, further theoretical considerations of Gravastars include the notion of a nest star, a second Gravastar nested within the first one. So that's the technical definition. I bet you're no wiser than I am. But the bottom line is that, and I'll read again, Mazur and Matola suggest that the violent creation of a Gravastar might be an explanation for the origin of our universe and many other universes, because all the matter from a collapsing star would implode through the central hole and explode into a new dimension and expand forever, which would be consistent with the current theories regarding the Big Bang.
Okay. So now that we know what it is,
yeah,
do you think they exist, and will we ever find one?
No and no, basically. It's an alternative theory for the Big Bang, and it's certainly interesting. And I think Gregor's asked us to talk about it, and now we have. so that's perhaps doing the best we can. Yeah. Interesting. There's just one other sentence I might like to read, if I can find it. I've lost it now. Oh yeah, the new dimension that will be created in this implosion, the new dimension exerts an outward pressure on the Bose-Einstein condensate layer and prevents it from collapsing further. So the Bose-Einstein condensate, it sounds as though that's this thin crust that it's got rather than an event horizon. And the Bose-Einstein condensate is really interesting. I think we've just celebrated, is it the 30th anniversary of the first example of a Bose-Einstein condensate being produced? I think that's right. I think it's 30 years. I think it's 1995. What is it? It's a condensation of atoms at very low temperature that behave like one quantum object. That's the crucial thing. So it's almost like entanglement, Andrew, where you've got quantum particles being entangled. This is a whole bunch of stuff that is so entangled it just looks like one quantum object, and we can now create them. So that's what they're saying, that maybe this thing is made of a Bose-Einstein condensate. I think this is a really good way to end the year's Space Nuts episode, because it is completely off the wall and talking about stuff that is right at the cutting edge of physics, which I love.
Indeed. Thank you for your questions, Gergo, and hope you're well. Good to hear from you. He's sent in questions before, so it's nice to catch up. In fact, I think Ishtok has sent questions in before as well. But thank you for your questions, everybody, for contributing to this, the final episode of 2025. Keep the questions coming in, because we're coming back next year, and we'll need some fresh stuff, because we're down to the last one or two. Which I didn't use because they all came from the same source, and I like to spread the love a bit. So we'll get into those next year. But go to our website if you'd like to send a question in. Click on the AMA link at the top, and you can send text and audio questions there. As always, please remember to tell us who you are and where you're from. While you're on the website, check out how you might be able to support us through various channels, whatever you choose or don't choose to. We're not going to make you do it. You can check out the shop as well. That's another way of supporting us. and so on and so forth.
I think, Andrew, while you're talking about the questions, I think we've got a pending one still from Rusty, which we should have, so we'll take it next year.
Yes. I recall that, but I thought we'd sit on it till the new year because reading the question will actually take the pulp of the episode.
Thank you, Andrew. Sorry to interrupt you there.
That's okay. No, that's okay. I just want to say thank you to you, Fred. And I should also thank Jonty because he did a fair chunk of the show. And we also had our guest presenter, Heidi, while I was away. So thank you to Heidi for her amazing contribution because it really saved my back because there was probably no way in the world I could have recorded from a cruise ship and got away with it. But fantastic. We've got a great team, and bring on the next year of Space Nuts. And I give him a hard time every week, I do, but I've got to say thanks to Hugh in the studio for his amazing work. It's not just our podcast that he looks after. He's got a whole stable of them, and it's basically a full-time job trying to run all this. And, there's not much money in it, but there's certainly joy in putting our skills into something in our semi-retirement from radio. So, But also, without the audience, we would be nothing. So we send out our thanks. We are so grateful to have you behind us. And I do keep an eye on the audience through the Space Nuts podcast group on Facebook because they spend a lot of time there talking to each other, sharing pictures, and posing unusual questions, which occasionally we will bring up on the show. And special thanks to our sponsors. We've had a few sponsors who've been with us for quite some time now, and obviously we're doing something right if they're willing to stick with us. So very much appreciated. Thank you, Fred. Thank you, Geordie, and we'll talk to you in the new year.
Sounds great. Look forward to it, Andrew, and all the very best for the festive season to you.
And to you, Amani. Thank you very much. Professor Fred Watson, Astronomer at Large. And from me, Andrew Dunkley, have a great Christmas, a happy new year, and we'll see you in 2026. Until then, bye-bye.
Space Nuts. You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Available at Apple Podcasts, Spotify, iHeartRadio, or your favorite podcast player. You can also stream on demand at Bytes.com.
This has been another quality podcast production from Bytes.com.